In this video, I will be going over L'Hopital's rule. This rule states that if f and g are differentiable functions and the derivative of g is not equal to 0, and we have the limit as x goes to a of f of x over g of x equals 0 over 0 or infinity over infinity. And these would both be considered indeterminate form. Then the limit as x goes to a of f over g is the same as the limit as x goes to a of f prime of x over g prime of x. So this just means that if we get 0 over 0 or infinity over infinity, you take the derivative of top and bottom and then plug in a. Also, you're going to want to continue taking derivatives of the top and bottom if you still get infinity over infinity or 0 over 0. And remember that g prime cannot equal 0. For my first example, I have the limit as x goes to pi over 2 from the right of cosine x divided by 1 minus sine x. So if we try plugging in pi over 2, we get cosine pi over 2 divided by 1 minus sine of pi over 2. So cosine pi over 2 is 0 and sine pi over 2 is 1. So we're going to get 0 over 0. So now we know we can use L'Hopital rules. And we can take the derivative of top and bottom. So we get the limit as x goes to pi over 2 from the right of the derivative of the top and the derivative of the bottom. And the derivative of cosine x is going to be negative sine x. And then your 1 will disappear, and derivative of negative sine x is negative cosine x. So now we have the limit as x goes to pi over 2 from the right, and we can cancel out those negatives and rewrite that as tan x. And here I'm going to solve this by looking at the graph. So the graph of tangent x is a periodic odd function with its asymptotes at negative x equals negative pi over 2 for the vertical, and also at x equals pi over 2. And since we're looking at pi over 2 from the right-hand side of tan x, we notice that this function goes towards negative infinity. So our answer will be negative infinity. For the next example, I have the limit as x goes to infinity of ln x divided by the square root of x. So as we can see, we'll get ln infinity divided by the square root of infinity. That's just two large numbers being divided. So we're going to use L'Hopital. So I'll take the derivative of the top. So I want the derivative of ln x, and take the derivative of the bottom. So the derivative of ln x is 1 over x, and the derivative of the square root of x is 1 divided by 2 times the square root of x. So now I can rewrite this as 1 over x divided by 1 over 2 times the square root of x. And when dividing fractions, we flip the second number and multiply. So I get the limit as x goes to infinity of 2 times the square root of x over x. I can write that as x to the 1/2, and then we can subtract the exponents. So I'm left with 2 divided by the square root of x as x goes to infinity. Any number divided by infinity will equal 0 or approach 0. Now for my next example, I have the limit as x goes to infinity of x cubed times e to the negative x squared. So first we're going to want to rewrite this as a fraction so that we can see whether it's in indeterminate form. So I can write this as the limit as x goes to infinity of x cubed divided by e to the x squared. And this is because when we have a negative power, if we bring it to the denominator, we can make the power positive. And now I see that if I were to plug in infinity, I would get infinity over infinity. So I know to take the derivative of the top and bottom at this point. The derivative of the top is going to be 3x squared. And then the derivative of an exponential is always going to be itself and then multiplied by the derivative using the chain rule. So we have 2x times e to the x squared because we took the derivative of x squared. So now we can cancel those x terms and we get the limit as x goes to infinity of 3x divided by 2 times e to the x squared. We're going to apply L'Hopital one more time and take the derivative of top and bottom. So I have the limit as x goes to infinity of 3. And then on the denominator, I have 2 times 2x times e to the x squared. So then I get the limit as x goes to infinity of 3 divided by 4x times e to the x squared. So that's just 3 over infinity, which is 0. For my next example, I have the limit as x goes to 0 of cosecant x minus cotangent x. And as we can see, cosecant x is 1 divided by sine x, and cotangent x is cosine x divided by sine x. Since they have the same denominator, we can subtract the numerators. So I have the limit as x goes to 0 of 1 minus cosine x divided by sine x. And when I plug in 0 for x, I get 1 minus cosine 0 over sine 0. And that will get me 0 over 0, so I know to use L'Hopital. So I'm going to take the derivative of the numerator and the denominator, respectively. So the numerator will be sine x, and the denominator will be cosine x. And we plug in 0, and we get 0 divided by 1, or 0. We can also check this on a graph if we're to look at the limit as x goes to 0 of tangent x. We can see that when we look at this function, if we come from both the left and the right hand side, the limit as x goes to 0 is 0.